Yes, so the first set of lectures were all right, thanks, Kit. They were mainly on some of the technical aspects of machine learning, specifically when you apply them to molecules, because I mean the devil really lies in the details here, and you need some specialized models and features for material science and chemistry. Now, this one will be a little more applied. It will be related to the kind of questions I was getting to closer to the end of the previous one. So the way it's going to work is that we're going to have a recap where we will do, hmm, yes, and then so these are the few things that we're going to look at in our recap: features and models mainly, and then uh, after that we're going to move on with performing first principle level simulations with MLPs on realistic systems. So that will really factor in a lot of aspects. For instance, feature selection and data set selection. So let's get into it, and then we'll discuss some applications. All right. So just to do a quick recap, what we learned last time was that yes, machine learning frameworks are kind of black boxes. They're usually a mapping between your structure to the energy and the derivative of the energy. So basically, you start off with a structure, and at the end, you obtain the total energy, the derivative of the energy with respect to each of the displacements, which gives you the forces, as well as the derivative with respect to a volume change that gives you the stress tensor. And with that, you can perform a lot of your simulations. So what we tried to do last time was to really get inside this black box and understand how do these work. And we realized that there were two crucial steps. The first step was to take this information and convert it into a form which is easier to learn. And the way you do that is by taking your distances from each nuclei. You say that, well, my chemical environment is surrounded by the set of all the other atoms which are placed at certain distances or displacements or certain directions and distances from my nucleus. How do I represent it in a form which is easy to learn, yet retains some symmetries? And the way we do that is by going into these so-called symmetry functions. And that's just one example of features. And finally, for each atom, you get an n-dimensional representation, which encodes these, let's say, the entire chemical environment. It's a high-dimensional quantity, and it's on us to represent or to develop this. And the second half is that once we have this form, which has some physics in there, the necessary physics, but it's also easy to learn and use in a machine learning model, we build our models, and generally the models are made in a local manner so that you can just sum up the energies of each atom and then, all right, and get the total values. So again, a recap of what exactly are these features. Well, the idea is simple. You sit on a particular atom, and you can ask yourself, well, how many atoms are there at a particular distance roughly, or in a particular region of in a particular interval, for instance, between zero 0.5 and 2 angstroms. And what you can do is that you can center this Gaussian around this value and just evaluate the value of this Gaussian on all the atoms of a given type. So what this blue one will measure, let's say you are sitting on an oxygen atom and you're evaluating hydrogen atom, it will measure the number of hydrogen atoms which are maybe 1.2 angstrom. And that would basically, for water molecule, give you the two bonded oxygens, right? And then this one would tell you how many are there at around 2 angstroms, which could include, the hydrogens from the next neighbor of water molecules and so on. Now, the other thing you should include, because this is purely a two-body descriptor, and from the vast amount of research on force fields, we know that pure two-body descriptors are not enough. Generally, you need 3 or 4 body descriptors. What you do is that you say, well, I will also probe how triplets of atoms behave around my central atom. And the way you do that is by asking the same questions that, okay, at around a particular distance, how many atoms are there at a particular angle, For example, if you look at this particular dark maroon curve, what it will really measure is that are there sort of straight line based triplets which say have certain distances between each other, and in that case you would basically be probing only the number of straight line-ish triplets. What you do with these wider Gaussians is that you keep accumulating everything which is not really a straight line, but something rather flexible, which also includes up to, let's say, 60 degrees or something. And similarly, you could do the other way around where you probe angles on the other side, and you can develop these in a way that you are kind of uniformly sampling the angular space as well as the radial space around the atom. Those are the two aspects. And third is more of a convenience aspect, and the fact that we will have to run molecular dynamics or geometry optimizations or compute phonons. So these representations better be smoothly varying. You don't want them to change abruptly. So that's why generally you have these cutoffs or functions which basically go to zero beyond a certain distance. For example, you can see that everything beyond 6 angstrom is definitely zero. In this case, unsurprisingly, that was our cutoff that we chose, right? So you have these three things: n-body correlation functions, two-body correlation functions, three-body correlation functions, as well as a cutoff. And that builds your features for the Beller-Pinello framework. All right. Next.
Sorry, could you just remind?
Yes, please
go ahead. Could you just remind me what the IJK in that summation was?
Right here?
Yeah, in the angular one.
All right. Yes. So for example, in this case, let me first start here. So if you are measuring G radial I mu, what it really means here is that for a given central atom I, how many atom types of mu, let's say, are surrounded around it, and in that case, Rij would be the distance between the neighbors of atom I. All right. Now, if you do this, what you're really doing here is that you're asking around a central atom I, how many triplets are possible. So for example, if you have one let me just use something. Yeah, and yeah, some annotation maybe. Yeah, so if you have a central atom here, and you have another atom here and another atom here, then this is I, this is J, and this is K. All right. In this case, I would be a central atom and J and K. And in that case, what you would really compute is this cosine of the theta, so this angle, and Rij would be this distance, and Rik would be this distance. Okay. So what this probes is essentially, this particular angle as well as distances. So if you have triplets subtending a certain angle, which are really far away, they won't contribute. So somehow this essentially gives you short-ranged three-body correlation functions by construction, so that only the triplets which are close to each other will contribute more. Yeah, is that clear?
Yeah, thank you.
All right, you're welcome. And of course, pardon my drawing. Yes, so again, to give an example, let's say you have this hydrogen atom and you want to compute all its features, So you start off as an input to this as all the position vectors of atoms in its neighborhood. So that would mean this particular position vector, this one, this one, this one, this one. All right. Now you have this set for this, and you start computing these radial symmetry functions. This is going to probe the number of atoms closely around this around this particular value. This will probe something around this value, this, and this, and so on. So within a radius, this will really tell you what exactly is the density distribution of all the other atom, for this given structure, right? And again, you will compute the angular symmetry functions, again, pardon this should be ANG instead of RAD. In that case, what you will be doing is instead of computing distances, you would be computing the dot product between two position vectors, and that gives you a sense of what is the, and that gives you basically a sense of what kind of triplets do you form, what are the angles that you generally probe, and you can construct these angular symmetry functions to either select for particular angles, that you can ask how many of 60-degree angles are there, or you can probe them in a way that they include the, let's say, sums of all sorts of angles, and that's your choice. So long story short, if you sit on this and create a circle, a sphere of 6 angstrom radius, and compute all the position vectors of all the atoms, you can recast that as a 17, I think this was 17 if I remember, 17-dimensional vector, where the first, let's say, 8 or 9 of them would give you information on how atoms are arranged at particular distances around the central atom, and the rest would give you information on how triplets of atoms are arranged. And that becomes your representation, or that becomes your feature on which you will learn. Okay. Now note that you have to compute this for every atom. So if you have if you have a water molecule, you need to compute this for the first hydrogen, for the second hydrogen, and then you need to compute the symmetry functions for the oxygen as well, right? So you will get, in this case, 17 or 3 by 17 dimensional matrix, which would give you the features for the entire structure, right? If it's a bulk system, then that would really be the number of atoms times the dimensionality of the feature. Is that clear to everyone? All right. And of course, the same thing you would do depending on whatever system you are in. So in this case, for example, if you have bulk water, you might probe certain values. And if you probe the same around a protein, they may be different, because the chemical environment would be different. And the idea is that this difference should be enough to tell you what is the energy of the structure. All right, the next part is the model, having represented your data into this abstract form, which somehow still respects the symmetries of your system, but contains the crucial information which could map with the energy. You say that, well, I know what is the chemical environment around my atom. I'm not going to ask what is the total energy of my system. I'm just going to ask, for this chemical environment, what exactly is the energy of my central atom, right? That is a much easier problem to work with, right? So at the end, for example, for your water molecule, when you have your features or representations for the first hydrogen, you would be asking, what exactly is the energy of that hydrogen, given that certain other hydrogens are at this distance, and certain other oxygens are at this distance, and certain triplets of HOH or HHO are at this angle and this distance. And that would give you the energy of that particular hydrogen. You do the same on the other hydrogen, and then you do the same on the oxygen. Ask, for this set of distances and angles and so on, for this abstraction of my chemical environment, what should be the energy of my particular oxygen? You add all of them up, and there you go, right? And what exactly are these models? It could be something as simple as a linear regressor to something as convoluted, excuse me, as say a graph neural network, which is what we'll see later on. Okay. So if these two aspects, are these two aspects clear? Does anybody have any questions? So let's do a recap, and let's try to disentangle approaches on this basis of what are the features and what are the models. So for the Baylor-Pinello scheme, which we have used as an example, we take our position vectors or displacement vectors around a central atom, and we construct these so-called radial and angular symmetry functions, right? Those are our features.
Sorry,
and,
sorry, I just have a question about the previous.
Yes. Yeah.
When you said that the sum of the local energies equates to the total energy,
Right.
Is there not like are we not is there not overlap between like the interactions that we're considering? Like, for example, if the hydrogen in one local environment, we're considering the interaction of that with an oxygen in another environment.
Right.
When we then consider the oxygen environment, we would also consider the like we would doubly consider the interactions. Is there not like a term that takes that away or something?
That's a very good question. And the answer is, for a small system's size, you would have these terms, but one can show that such terms in the large system size limit would go to 0. So the way you can think about this is that you have a dominant term. Let's say that you can divide your, maybe I can use something like this. Yeah. And again, you will have to use your, imagination here, but let me preface that by saying this is an ansatz that we use, So this is an approximation. Generally, it is not necessary for your total energy to be strictly additive for a small system. You may have non-additive components as well, but this is what we assume. And the reason for that is on the basis of thermodynamics. Let's say you have a system, and you split it into various blocks, 1, 2, 3, 4. Now you can say that the total energy is the energy of this block 1 plus block 2 plus block 3 plus block 4. And I'm already regretting using 4 blocks instead of 2, plus the surface energies, which essentially would mean the interaction between 1 and 2, 1 and 3, 2 and 4, 3 and 4. Now, if you really think about it, the energy of 1 would scale with the volume, right? Because one could say that, well, the energy of 1 should really depend on the number of atoms or entities which are in 1. While the energy between 1 and 2 would scale with the area, right? So there's a term which scales with r cube, and then there's a term which scales as r square, essentially. This is more of a back of an envelope type analysis. And you can say that, well, in the limit that r tends to infinity, the other way of thinking about it is that you divide it by r cube, and then you take the limit of r tending to infinity, and then you will get the bulk terms, and then you'll get the so-called interaction terms with the 1 over r, and you can say for a large enough r, for my thermodynamic analysis, this term will go to 0. So that is more of a thermodynamic argument why energy should be additive, because the components which will give you these bulk terms, which will be much larger than your surface terms. And this is more of an ansatz that we use here, You say that, well, if this has to be true in the thermodynamic limit, I'm going to use exactly the same here in this case. And yeah, so that is my answer to you. A short technical answer could be that, for example, if you are double counting, in case you are, then that double counting can be avoided through some prefactors, like in a Leonard-Jones term. You can always have a 1 over half term, which can account for this double counting, right? And since you are regressing everything to minimize these errors, any terms like this, which could potentially double count, would have the right prefactors. Have I satisfactorily answered your question, Savya?
Yeah, that makes sense. Thank you.
All right. Okay. Thanks for the question. And again, pardon my drawing. Yeah. Okay. So up until now, we have discussed these, that yes, we use angular and radial symmetry functions, and then we use a simple artificial neural network setup to regress. What exactly is an artificial neural network? Well, it's the most basic thing. You have an input layer and an output layer, and in between you sandwich a hidden layer, and that really is enough to make this whole thing work, because you've taken your data and you've processed that into something sensible, something which respects the symmetry of the system, something which has some physical intuition, and is easily and something which regresses easily with your total energy. And that's why a simple enough model is okay. Now, have people heard about the gap potential? If so, can somebody tell me what are the features of a gap potential and what is the model that they use? Anyone? You have 5 seconds, because we would have to move on as well. Okay, I'll tell you.
I think you
Yeah,
mentioned
go on.
it. I think you mentioned it last time. And I also just came up on the slide just now, but it was a kernel model.
And what about the features?
I don't remember that. Sorry.
All right. So I can just tell you that just like in the case of symmetry functions, we constructed them, in the case of a gap potential, you can show that, well, you don't really have to do these summations explicitly. Hold on, I have something in chat. Yeah, so kernel ridge regression or Gaussian process. So Kit, your answer is right. Yeah, and what you can do is that you can do a spherical harmonics expansion around your central atom. Now, if somebody is not sure how that really relates, you can just say that, well, the first component of the spherical harmonic expansion just tells you how many, it is a radial component because it just probes, it approximates your density with a sphere, right? Or a Gaussian, basically. So it encodes the radial term. And as soon as you include the L is equal to 1 term, it also encodes some dimension, some directionality. Now you can represent your total density as a sphere plus some additional perturbations along directions. In fact, along any direction with that. And then if you take L is equal to 2, you can actually encode two. You can also encode two body terms in this case. So all in all, you can show that if you do this spherical harmonic expansion and you try to do a bit of gymnastics with algebra, you can come up with 2 and 3 body correlation functions, which are very much similar to radial and angular symmetry functions, but they can be systematically improved to cover the entire 2 to 3 body space. So they are more systematic, you could say. What's the next one? I've forgotten. Yeah. What about deep MD? Does anybody know? Let's try to get to the more fancy machine learning architectures and see whether we can disentangle them. You can guess as well. Yes, so you're right, but what about the features? So that's the thing. As soon as you get to the more fancy deep learning based architectures, you can almost start getting the feeling, well, whatever we did with Bella Pinello was actually useless because, if you use a deep learning model, you just throw data at it, it'll all work out. That's actually not true at all. You really need to get into the details of all of these approaches. And you can actually show DeepMD also uses radial and angular symmetry functions. Their architecture is essentially the same as Bella Pinello, just that they call the step from going from your structures to these symmetry functions as embeddings. That's, let's say, the lingo that is used more in terms of machine learning. It's a more general term. And their construction of these radial and angular symmetry functions is, let's say, more universal than in the Bella Pinello scheme, but it's exactly the same. And instead of an artificial neural network, you just use more layers in this case, and that does the trick. Schnet, actually, another deep learning based approach which uses a graph neural network, is only based on 2 body distances. So it's a pure 2 body descriptor. And of course, you can construct some 3 body correlation functions based on just distances. So it can span 2 body completely and 3 body partially, and that's basically what it's based on. Even though it just takes positions as input, it actually transforms that into distances and then works. And finally, we have the latest ones, something that you might all have thought about or considered, which is Anyquip and Mace. The beauty of these approaches is that they can go up to an n body descriptor, so they don't really truncate up to 2 and 3 body. And they are all based on a very nice recursive relation based on angular momentum quantum mechanics. If anybody is interested, let me know, I can share the papers. But yeah, these are all very nice. The only difference is that in the case of Anyquip, you really start with all the displacement vectors, and you try to regress on those. Yes, I have something in chat. No, it's just plain distances, Nick. There is no direction. If actually, that's the thing. If you just take I can tell you the reason as well. Let me just finish the bit on this. So what Anyquip does is that it actually takes the vectors and tries to work with that. So what you can think of Anyquip as basically Schnet, where instead of distances as your input, you use displacement vectors. Now the problem is that distances are very nice, if you rotate your atoms, if you translate your atoms and so on, your distances won't change, So you can come up with a very simple architecture. When you work with displacement vectors, as soon as you start rotating your atoms, they will also rotate. So displacement vectors have some symmetries that they respect, and that's the SO3 group. And that is why you need to use an architecture which respects these symmetries, which is equivariant to these symmetries, which means that it has it if it if something is equivariant, it means that it can be both invariant. So you can construct terms which will not change if you make some sort of changes along a particular symmetry group. But then you can also construct abstract quantities which will also rotate in the same way or have exactly the same symmetries as your input, right? So basically, Schnedt uses distances, Anyquip uses displacement vectors, and the only way to make this work is to make sure your architecture also rotates with the displacement vectors, and that was the novelty there. And what Mace does is that instead of displacement vectors, and a really complicated architecture, it uses spherical harmonics based low dimensional features, and it constructs recursively these high body ones. So you can show that, with low spherical harmonic descriptors and some semblance of directionality, you can construct anything from that. Okay, so this was just a very high level discussion on all of the approaches. The bottom line here is that don't be misguided by the fact that certain methods are end-to-end. That means that they don't encode any of what we have learned. Well, all the approaches are really based on going to a feature space, which is an n-body correlation function, and then applying a model. If you use extremely simple things like two-body distances, displacement, or something like an L is equal, or just a spherical Gaussian and some distances, you will have to use a more complicated model. But if you use some more sophisticated features, you can get away with a very simple model. Like a kernel ridge regression is actually a linear regression, So it's really that. So yeah, this is where we end the recap, and I hope it was worth it. If you have any questions, now is the time. Okay, that was a great feedback. Exactly what every person expects after they and do some enthusiastic teaching. All right, let's move on. It could only mean that you all have understood everything. So yes, the next bit that I'm going to discuss is that now we are in a situation where we can get our total energies and forces in a very cheap manner, and how about we explore some more sophisticated simulation approaches? So I'll just do a little bit of theory just to introduce you to something, and then we will look at application, because I know that most of you know about molecular dynamics or may have heard of it. Not many of you may know about the path integral framework, and don't worry, it may sound daunting. It's actually extremely simple. I'll try my best to explain it in a very simple way. Now, what's the difference? Okay, let me ask, what are the main approximations that we take when we do molecular dynamics? I would like to ask this question directly to the people here.
Born-Oppenheimer approximation.
Yes, so that's one of the central approximations, which is that you decouple the dynamics of your electrons and nuclei. What you say is that, well, if I displace my nuclei on a time scale of a femtosecond, my electrons would have already relaxed, let's say, at an attosecond time scale. So there is no point including the coupling between their dynamics. So you just say, well, I move my nuclei, my electrons have already relaxed. Let's just compute, the expectation value of the energy and use that to drive my dynamics. And then what else? There are some more approximations.
I guess you're approximating your nuclei moving classically rather than quantumly.
Yes, so that is one of the major approximations in ab initio MD, that after you get your forces, you drive your dynamics in a Newtonian manner, or you treat atoms as billiard balls. Now, electrons are quantum, but let me uh, give you this harsh reality. Some nuclei can also behave quantum mechanically, especially protons. And we'll see a few examples where they actually do. So the question is, how do you include the quantum nature of nuclei? You could try to solve the vibrational Schrodinger's equation, and if anything that electronic structure has taught us is that that will be painful. So the path integral method is something which allows you to perform quantum nuclear motion in a classical manner. And what exactly does that tell you? Well, if you have a quantum particle at a temperature T, then its thermodynamics or its statistical mechanics can be described exactly, if they are distinguishable, by a ring polymer, which is purely classical. And what exactly is this ring polymer? It is just the same atom or same system repeated p times. Consecutive atoms are linked with a spring, which depends on p, and the temperature of the system is p times elevated. Okay. So as I've written, a quantum particle is statistically same as a classical ring polymer made up of p replicas of the particle at p times the temperature. And actually, of course, I've skipped many steps. You can't prove it in 3 lines. But the main idea here is that, well, in terms of quantum mechanics, my partition function is not the regular phase space integral that we're used to. It's actually the trace of the Boltzmann operator. And to really be able to compute this trace, you need to know the eigenstates, which would be challenging because it would require solving the Schrodinger's equation. Instead, if you can write this as this particular term, and then you perform this sort of approximation, this is called a Trotter splitting of an exponential, and this is exact, in the limit of p tending to infinity. Then it can be shown that you can compute this trace in the basis of positions, and that gives you a purely classical expression, which is this one, right? So we have started off from the quantum partition function, and I'm asking you to believe me that by doing this and by computing this in the position basis, you can show that this is basically a classical system. Yes, and this is really exact in the p tending to infinity limit, right? Now, what exactly does this Hamiltonian look like? Well, if you hide this term for a second, then it's basically the kinetic energy of one of the replicas of your particle and the potential energy of one of the replicas of your particle, right? So independent p systems. Now, as soon as you include this middle term, it has a spring that connects the j and the j plus 1 replica. So basically all of these spring terms. And as you can see, this spring depends on the Planck's constant and the temperature, right? Now let us do some simple analysis. If your Planck constant goes to 0, which means that you take the classical limit, then this term would go up to infinity, right? That means all of these springs would compress immediately, and this entire ring polymer would shrink to one particle. So essentially, this would get approximated to your classical system because you now still have p replicas, but they're all exactly at the same point because your springs are so tight. So this leads us exactly to the classical limit. Now let's take the other limit in which your temperature goes to 0, right? And in that case, this will go to, let's take the other limit where your temperature goes to infinity. So high temperature is also the classical limit. And again, the spring would become extremely stiff and your entire ring polymer would collapse to one classical particle, right? Now, when these are not 0, your system would, let's say each replica at a given point of simulation time, you won't have one position, but you would have an ensemble of positions, right? And somehow you can think of it as this ring polymer at every point gives you an uncertainty in your positions. So somehow by replacing one particle with this chain of particles, which are not completely independent, you can get, let's say, the delocalization of atoms in your simulations, right? Now, generally you have to converge. So there's only one catch, which is that it is exact in the p tending to infinity limit, and generally to make this work, you have to converge the value of p for a real system. Does anybody have any question here?
Yes, sorry. The potential energy, that VQJ term, is that just
Right.
essentially like your Born-Oppenheimer
Exactly.
potential energy?
Yeah.
Yeah.
So in each every replica of a system will experience its Born-Oppenheimer potential, plus the atoms will experience the spring term.
So basically, it's kind of, you have a load of nuclei that are sort of exploring all the like possible configurations that the one nuclei could kind of explore.
Yes, and somehow the uncertainty in your position that you get is linked to rigorous quantum mechanics rather than just some random number. Yeah. Anybody else has a question? Please ask. If you have not understood anything, you can say that, and I can explain again.
Could you go over the previous slide?
Yeah. You have a specific question here?
Yeah.
Go on.
Why does the partition function here show that this is how you can treat it?
Okay, maybe I should have spent more time discussing that. So this is your quantum partition function, the trace of the Boltzmann operator. That is an identity. Okay. So what you're really saying when you compute the trace is that it will be, you can show that if you compute this in the basis of its eigenstates, and you operate this operator on the eigenstates, this will become exponential of minus beta e I, where I is ith eigenstate, and the trace will be a sum. So you can show that this will exactly be related to the exact quantum partition function. Now, is that understandable, that this would be the exact quantum partition function?
Yeah.
Okay. Now, if you write this, the Hamiltonian as T plus V, T is your kinetic energy and V is your potential energy, then it is not possible to do anything analytic any further because both T and V commute with each other. So you cannot write this simply as exponential of minus beta T times exponential of minus beta V. Okay. If you could do that, you would be able to work in the eigenstates of the position basis. So that would be much simpler, but you can't do that because both T and V commute, which means that if you write it as exponential of minus beta T times exponential of minus beta V, or the other way around, you would get different results. So this is not a unique way of writing it. However, if you raise this to the power of P and divide this to the power of P, so you basically write this as this term raised to the power of P raised to the power 1 over P, and then you absorb this 1 over P here, what you can say that, well, I am raising the temperature of my system. Okay. So if you multiply this by P and take if you multiply this by 1 over KBT by P and then take P over here, you've said that, well, I've written my partition function as a product of high temperature partition function, right? And then you can say, well, at high temperatures, T and V should not commute because in high temperatures, if my P is going to infinity, and this is really infinity, then I can write this as just a product of them, or in this slightly more fancy way, because at such a high temperature, there is no commutation. It's a classical limit, right? And then you get this particular expression, And then how do you compute this trace? That I cannot cover, but you will have to trust me that if you work this out in the basis of positions, so you integral over dq and work this out with quantum mechanics, you can show that this leads to this expression. And this, if you think about it, is the expression of a classical partition function because it's a phase space integral. So integral over dp dq exponential of minus beta h of p and q. So this really is a classical Hamiltonian, and if you perform an integral over its phase space with this particular factor, that gives you the partition function. So this is the expression of a quantum partition function. And what you have shown at the end here is that after a bit of algebra and gymnastics, you can show that it has a classical-like expression. So if you perform classical mechanics for this system, for this Hamiltonian, it will be equivalent to performing quantum mechanics for this. Is that clear or is that not clear?
Yeah, thank you.
All right. If you have a specific question, feel free to ask. Anybody else? Okay, so let's move on. Yes, so realistically, for each system, you have to converge the number of replicas, okay? For example, here I'm showing the difference between the classical and quantum potential energy for room temperature liquid water, where I've performed a simulation at a particular level of theory. P is equal to 1 basically means ab initio MD. And here P is equal to, by the time you get to P is equal to 32, which is that you simulate 32 replicas, you can start seeing that it actually converges to something, and that something should be the quantum limit of this particular thing. Now, what this really means is that instead of computing one total energy and force, you need to compute 32 potential energies and forces, right? Now, if you compute something different, like the heat capacity instead of the potential energy, you see that convergence is actually obtained at 128 replicas. So if you want to compute the heat capacity, your simulation will have to be 128 times more expensive, all right? Now, what that really means is that historically, path integral methods have been considered computationally expensive, much more than ab initio MD. They are extremely useful but costly, and a lot of work has gone into reducing the computational cost. My entire PhD was on that, and one of the things which is very good at reducing the cost is using a much lower cost of the potential energy surface. So if you, instead of using DFT, if you can use machine learning potentials, then that automatically gives you a reduction in the prefactor, and if you combine it with other cost reduction techniques, then you can show that this approach can become extremely computationally expensive, right? So the idea here was just to tell you that beyond molecular dynamics, there are other more advanced approaches available, which have so far not been used extensively, in the mainstream because they were costly. And with machine learning potential, that really opens this gate towards obtaining much more sophisticated estimations of any property that you would like. All right, so this was just a few slides on the theory of the path integral method. We might touch upon it a little later in the applications.
Sorry, just so
Yeah.
when you're actually carrying out this calculation, then say for the heat capacity of water, for every oxygen atom, you would have instead a ring of oxygen atoms,
right?
That 128 oxygen atoms in
Exactly.
that ring,
Right.
and then the 128 hydrogen atoms next to it. Okay, right, yeah, just and then okay, just making sure I got how you actually compute it.
Yeah, exactly. So you have 128 replicas of your system essentially, and somehow in these replicas are arranged such that most of the oxygen will be very close to one another, while the hydrogen will be slightly more distant because oxygen is heavier. It is less quantum mechanical. It exhibits smaller delocalization, while for protons it will be much higher.
Okay, and how do you distinguish between the ones that are like the oxygens that are the same oxygen really, and then the other oxygens nearby that, like, well, I guess with, when you're doing the ab initio method, they have that spring constant between them, but if you're using an artificial neural net, you don't have that spring constant between them.
Right. So
maybe you're going to go over this later. I don't know. Sorry.
Yeah. So no, I was not going to, because actually, when you do your ab initio MD, actually you don't have the spring constant. Maybe I was a little misleading. When you do ab initio MD, all you have is the potential energy. Actually, the spring constant doesn't depend on the potential. The spring constant depends on the number of replicas, the temperature, and the Planck's constant. It doesn't have any explicit dependence on the potential energy surface. Of course, when you start moving on the potential energy surface, depending on its shape, your ring polymer would arrange in a particular way and certain values would be more likely to happen, right? Is that clear?
Okay.
So essentially from your ab initio simulation, you would just be computing this, and this is dirt cheap to compute, So the total cost here is essentially the cost of computing this 128 times,
Okay.
Right? And what you can do is instead of computing this with an ab initio calculation, you could use a machine learning potential.
Okay, thank you.
So
All
I've
right.
just got a question as well.
Yeah, please.
So when you have, so let's say you have like an oxygen and hydrogen in your system,
Right.
and you've got your copies of your oxygen, you've got your copies of your hydrogen. Which, how do you calculate what like interaction do you use to calculate between the oxygen and hydrogen? So like which hydrogen do you use to calculate that interaction with the oxygen, if you get what I mean?
Yeah. I'm trying to look for something, which might answer this question. Okay, maybe I have. So this is what a PIMD simulation for a molecule of water will look like. Okay. So as you can see, this was a very short one. Your oxygens are extremely close, and your hydrogens are a little further. Now your question is great. It almost feels like you will have to simulate 128 times 128 times 128 replicas. Right?
Yeah.
But it's not the case. Actually, the path integral expression is very clear. You only have to simulate 128 replicas because this particular hydrogen atom will only interact with the oxygen which belongs to the same replica. So it's like parallel. Okay, I hate to use this analogy because it sounds really pseudo-scientific. But let me swallow my pride and say that it's like parallel universes, where every universe has a water molecule. But between these two universes, this hydrogen will interact with the hydrogen in the other parallel universes. But this hydrogen will not directly interact with the oxygen. Okay.
Right. Okay. So they only interact across replicas. Only like atoms interact across replicas.
Exactly. Yeah. And that's the advantage of disadvantage of not being a native English speaker, that I couldn't really say that. But thanks. I will remember that. Yeah. All right. So that really is the approach. All right. So yeah, to answer, it's just bookkeeping and you can code it up rather easily. Okay, now let's get to the reality of first principle simulation, and often we get to this extremely stressful situation where you start your PhD and you have two options. Either you start running an ab initio simulation of a really complicated system, or you have the task of developing a machine learning potential, and none of these are easy. Certainly machine learning potentials have come with this baggage of, that your entire PhD can go in, trying to develop one and so on, Thankfully, things have changed now, you don't need one PhD, you can actually do things in some cases, even in a week, or if you are completely new, I would say in a month, and if you're an expert overnight, so things have really improved. And what we're really going to discuss is take a set of realistic, complicated cases and see how do you handle the practicalities of developing these models. All right. Some case studies. Yeah. So here is one of the papers by one of my colleagues, Christoph Schran. It was published in PNAS recently. So what they have really shown is sort of a recipe. It's an entire framework which allows you to simulate systems of the complexity that you see. So these are all solid liquid interfaces and mostly water hydrophobic or hydrophilic interfaces, as well as some solutions. In this case, some ionic solutions. So like a fluoride ion in water, sulfate ion in water, and so on. So they asked themselves, how difficult could it be to come up with an approach which would work for all of these complicated systems? And as you can see, many of them have like 5 species or 4 species, which is very challenging. If you have really followed this field, you would see that mostly people deal with much simpler systems with 1 species or 3 maximum, and there you're already sweating. And the approach that they came up with was like, well, it's going to be extremely hard to develop a single potential, which let's say would be able to simulate all possible phases of water between carbon nanotubes or all possible radii of carbon nanotubes. So how about we take a particular problem and develop a machine learning potential just for that problem? So it was essentially a bit like that you want to run a particular ab initio MD simulation. Most likely, if you run a very long simulation or a very large box, you will have to wait until the end of your PhD for it to finish. So how about you run a short simulation on a small system size, use that to quickly train a machine learning potential, and then do much larger system sizes with that. So the first step is that you take your system. So let's say we take F minus ion in water. You take a small box, where the important thing is that if the cutoff of your model is 6 angstrom, you at least should have 12 by 12 by 12. That's the only thing. Okay. And you run ab initio MD for a short amount of time, and there, let's say you run it for a few picoseconds, 5 picoseconds or 10 picoseconds. You're not going to be able to get any or a lot of statistics out of this to compare against a very sophisticated experiment. But then what you do is that you take randomly 10 of these structures, and with these 10, you train not 1, but 8 models. So you take 10 structures at random from this simulation, and you train 8 models, on this. And then you predict these models on the entire trajectory, and you see what are the predictions and what are the disagreements between the models. The larger the disagreement, that means that the larger is the probability that the structure is nowhere in my training set, right? So in that, you only select the structures which have the highest disagreements or the highest errors, right? And you take 10 structures again, redo, and you do this. And at the end, you can show that with just 100 of these, you can get very low errors and cross the entire trajectory. And since you have only used, let's say, 10, 20, 30, 40, up to 100 structures, it's very easy to build and train these models, And finally, you can use a very tight convergence, either both at first principle level. So you take these structures, you redo the energy and force calculation at a high level of theory, and you really fit your machine learning potential down to the 8 decimal place in terms of its error, and you have your final model. And then you do your applications. What they showed that this entire procedure, if you automate this, could be done in less than 24 hours on, let's say, reasonably sized on let's say the typical supercomputer that you would use or a cluster that you would have. Now, what's the devil in what exactly are the details? Actually, in this case, the details were the simplicity. They did not try to go for anything extremely difficult. What they said, we'll choose very simple symmetry functions which just linearly probe, different intervals and fairly short range. And similarly, we'll just take very simple angular symmetry functions, just making sure that we probe all relevant distances and angles, and that was it, And what they show, and this is more of a framework with a code as well. So you just provide your ab initio trajectory. You have to do a few steps, and at the end you can get these kinds of plots. What these plots tell you is that you can compare the radial distribution functions of all pairs of atoms. Black would mean the reference ab initio trajectory, and dotted red is the machine learning model, the committee neural network. And you can see that they found it was extremely accurate with respect to structural descriptors. But then it also looks at dynamical properties. This is called the vibrational density of states, and what that really gives you, so some sort of a vibrational spectrum. And you can see that for every atom, you can compute this, and you can compute this and compare against the short ab initio trajectory. You can validate whether you have a good agreement or not. And finally, you get some metrics on how good are your force predictions per atom, because at the end of the day, your molecular dynamics is going to be driven by your forces and not your energies, right? So this was really the approach. And as you could see, a very simple approach and a good implementation is the key to, in this case, really being able to study a lot of really complicated systems, which were not possible before this. And just to be clear, the entire spectrum of systems include, let's say, a fluoride atom in water, sulfate in water, carbon nanotubes, boron nitride nanotubes, water between, let's say, confined water, as well as water on a titanium dioxide surface where it could potentially react as well. So from a very small trajectory, you can actually build really good models with which you can simulate large system sizes, enough to compare with experiments, and to obtain good statistics, and to obtain some reasonable conclusion about your system, and to study much more difficult problems as well, like water diffusion or water reactivity and so on. Anybody has any question here for this case study? Practical questions would do as well. So what do you think are the limitations of this approach? Let me ask some questions just to have some sort of a discussion. Anyone?
I guess transferability is an issue. You can't, if you just trained your model on an ab initio method where you've looked at one system, it's very difficult to transfer that to a different system.
Yeah, I agree with that. Although I would argue that was by design, so like they deliberately decided not to build a model for the entire, for all phases or for all temperatures and pressure, but to focus on something. But yes, but let's say, yeah, go on. It seems you have a comment. Yeah.
So I was just going to say, well, yeah. I guess then if you're trying to see phase transitions or more complicated processes, then it won't really work for those types of scenarios.
Probably exactly this particular framework, no, but aspects of it could be used. Yeah. So Kit, yeah, feel free to.
I found that because you have 3 n forces to every energy for every configuration you add, it's much easier to get a very good fit on the force and the dynamics of the system rather than actually the energy prediction. That's a short.
Yes. So yeah, but so that could be, even though I would say for yes, but can you tell? So I would say that the kind of errors you could expect on your energies would more likely be some sort of prefactor like expressions, So let's say you could have some sort of a rigid shift around that. But I feel like if your forces are correct, that means the derivative of your energy is correct. And derivative is basically a change in your energy, right? Yeah. So your relative energies are still fine when you do forces, right? So,
yeah,
most of
the energy gap's usually pretty consistent, but which is okay because that's where we kind of operate with DFT anyway. You want energy cancellation, so right,
exactly. And most of the observables are related to differences of energy. So you could say that with forces you could still reasonably get them right, But yeah, I mean, yes, you do train on forces, so the error in your energy would be larger. Yes.
Yeah. Other than that, I don't really know what the flaws are. It's quite quick.
All right, so let me ask certain questions to you all. How do you think this approach is going to scale with the number of chemical species? Well, Kit, you're unmuted. Do you want to say something?
How will it scale?
In the sense, yeah.
So,
Yeah, exactly that. Yeah.
how will it scale with more species?
Right. Let's say you have a high entropy alloy with 8 particular elements, and you want to simulate it.
The more elements you have, the more symmetry functions you have to compute. So it probably scales in some kind of exponential way with the number of symmetry functions.
Yes, so that can be seen as one of the limitations. That's more to do with the Bell-Pinello scheme, that the more are your number of elements, the more would be the number of combinations, and there you would have a problem. Yeah, so I agree with that. Is there one more thing that, let's say, what do you think is do you think it is cheap? Can you comment on the cost of generating the training data? Anyone?
It's expensive.
So yeah, so that could be another. So you could say that, well, you need an ab initio trajectory. Maybe, for my system, I need a very sophisticated density functional or level of theory, and it's expensive, right?
Well, I mean, a way of avoiding that would be, for instance, with the fluoride ion, you use a force field, a parameterized force field for chloride solution. It gives you some example configurations, which you then do
exactly
EFT on the single point. You can parallelize that. You don't have any kind of time dependence to the steps. And it's quick.
Yeah, exactly. So that's a very good answer. So one way to go beyond this is to not use an ab initio MD, but something like a surrogate, like a force field, if you think it's good enough, or a lower level of theory, just to get some initial sampling, and so on. So there are many possible ways going about it. But I would say that the same framework could potentially be used, for a lot of things. For example, if one could improve the model of, which doesn't have this exponential dependence. For example, May's model has this property where they have constructed it in a way that it doesn't really scale with the number of elements. And that shows promise, although we are still yet to see how well it will do on these systems, but that's at least something promising. And yes, on this side, by using more surrogate models, which are all right, you could potentially alleviate or attenuate some of these. But I think it's still worth looking at how good a simple approach could yield, in terms of accuracy and robustness of the system. All right, so this was, I think, and also practically speaking, many of you may have cases where, you want to understand, well, what would have happened if I had a longer simulation or a larger system? And for those cases, this is really the setup to go with. If you already have run some short ab initio MD and you would like to scale it up, then this really is the approach for you. I would highly recommend this. All right. So the next case study that I will do is more of an application, something which I have been very much interested in. I'm sure some of you are too. It's structure prediction, crystal structure prediction of molecular crystals particularly. And why is this important? Or why is this interesting? Well, because a lot of materials around us are actually crystalline substances which use small molecules as building blocks. And I like to use this analogy where you have these Lego blocks and you can build a structure. In the same way, you can think of these Lego blocks as small molecules, and the way you build your structures, molecular crystals are exactly that. The way you arrange these particular crystals, the way you pack them can give you a different crystal. And depending on the way in which you pack and depending on the property of your molecule, you could have a versatile class of solid. So you could have a lot of properties ranging from the food industry to electronics. And of course, we all know molecules are important in the pharmaceutical industry, right? Now, what exactly are the challenges here? And of course, this is more of a broad topic. Many of these challenges also occur in ionic structure prediction, or when you want to look at absorption of molecules or interfaces. That generally we deal with many possible structures, and these structures can be very close to each other in terms of their energies, right? So for example, this is just an example that paracetamol can have many different possible arrangements of molecules, And they can be extremely close in terms of their stabilities. For example, if you compute the free energies somehow, which can be done by, let's say, computing solvation energies of these, and you might ask yourself, why isn't so much data on relative free energies is available, even the pharmaceutical industry has so many of these polymorphs? And yeah, that is something slightly disappointing, that many of these companies don't reveal, this data. But if you had this data, you would see that the free energies between, or free energy differences, or solvation enthalpies between these structures are extremely close, down to, let's say, a few kilojoules per mole. And what that really means is that from the perspective of simulation, it's an extremely difficult task of saying, okay, this structure is really the most stable one. Because if you make small changes in it, the next structure that you would get might have an energy very close. And many times these small energy differences can be greater than the error in your density functional or the error in your sampling technique, And here is just, you may have seen this. I like to use this a lot. And that's mainly because I personally feel like a lot of focus is made on the errors arising from the level of interaction energies, that you have. But equally important are the level of treatment of your motion of atoms, whether you take them as static molecules or harmonic crystals, or you include, full anharmonicity with ab initio or path integral molecular dynamics, really will also affect, this. So for instance, if you look at current approaches, you can look at them as combinations of DFT and a type of sampling technique. For example, this is a very nice paper where they try to look at glycine, and they showed that you really have to go to a hybrid functional level of theory, and only then, you can get qualitatively correct relative stabilities of glycine polymorphs. And as you can see, the dashed lines here are the experimental relative stabilities. You can see how close they are to each other and how difficult this could be from simulation perspective. For example, in this case, they used a hybrid functional, but then they used purely static calculations at the hybrid functional level. And to get the 0-point energy, they did a harmonic calculation, but at a much lower level of theory. On the other hand, you have this very nice paper where they try to scale up correlated electronic structure methods like coupled cluster, diffusion Monte Carlo, and the random phase approximation with some corrections. And of course, here you can see DMC. I've put this in the same category as MP2, but actually DMC is much more expensive and much more sophisticated. So what they have really tackled this is this problem of relative stabilities. Even though they have used static atoms, they have gone to very high levels of theory. But still, let's say the end goal in terms of molecular simulation is to really be able to combine these two, so that you can eliminate the errors, arising from both of these. For example, the only way you can make a prediction comparison with the experiment is to subtract out, let's say, 0-point energies from thermodynamic data and extrapolate them to 0 Kelvin. And the way you do that is using some density functional theory based harmonic calculation. So using a different density functional theory, you could get a slightly different agreement or disagreement. So long story short, to really be able to nail these, and say exactly why they and to what extent they match with experiment, you need to have some sampling as well, right? Now, some of the case studies that I'm going to show are on the use of machine learning methods, along both the axes. In some cases, machine learning methods will be used to get robust models which try to get cheap estimates of your interaction energies at a first principles level, and then apply it to very large and complicated systems. And then on the other side, we'll look at how do you take some of the structures and try to do both ab initio MD and combine it with, let's say, a hybrid functional calculation and get direct free energies, right? In the first case, there is a very nice paper from the group of Professor Garbarchani in Cambridge, where they have tried to compute the total, let's say, the binding energy of a molecular crystal by breaking that down into an intermolecular intramolecular term and an intermolecular contribution, right? So so basically it's the energy of a particular molecule plus, let's say, an intermolecular energy that tells you what is the energy of embedding this in this matrix of others, And the reason why they chose two different models, one to learn the intramolecular and one to learn the intermolecular energies, is because they have very different energy scales. Intermolecular interactions are generally extremely slowly varying and smaller in magnitude, while intramolecular ones, for example, if you change the bond length, that would lead to a very large change in energy. So arguably, if you try to learn them together, you might get a very good description of intramolecular interactions, but your error might be comparable to intermolecular ones. So that was the basic idea of doing, let's say, a range separation here. Additionally, instead of learning, because they really try to apply it to a large class of systems, instead of learning it directly, what they try to learn is the difference between the total energy and the predicted energy using a tight binding model. A tight binding model is like a semi-empirical description. So they use some sort of delta learning scheme where you don't directly learn the full binding energy. You learn the difference between the binding energy predicted by a surrogate model or a lower level model, and you only learn the difference, which is much easier to learn because it's smoother. And they managed to predict it on a large set of molecular crystals. And what they have correlated here is the ranking order obtained using, a reference approach, and the ranking of all the polymorphs of this crystal obtained using their approach. And you can see that overall there is a positive correlation here. And the long story short, here what you can conclude is that you can actually build these models. And since generally you can show that there are millions of possible structures, when you want to take the set and reduce it down to, let's say, a few hundreds or a few tens, such an approach could be extremely useful. Right. Again, just some numbers on how efficient these models are. So if you use density functional theory plus many body dispersion, you need like 3,000 hours to do a crystal relaxation. We're talking about computational time here. And if you use density functional tight binding plus some dispersion correction, which is your baseline, you need like 6 hours, and with the gap potential, it just takes 0.1 hours to do a prediction. So here are basically the number of crystals for 10,000 crystals. What would be the total times? So this kind of tells you the amount of time that you save, by adopting an approach like this. Yes. So does anybody have any question here? None? Shall I ask the same questions? Yeah. What could be, a limitation of such an approach?
I don't know. Maybe if the intermolecular forces
hold on.
correlated with
Hold on. I think there was one more person. Was it Felix?
I was.
Yeah. So sorry, Jamie. I just thought a new person would be good to have, speaking, and then we can get to you. Go on.
Since you said it would be dependent on the delta, if or the difference between tight binding and so if that difference is for some reason, maybe because tight binding. I mean, I'm not too familiar with it, but like if that doesn't work out well for that particular system, we don't know the difference, or maybe it's unusually high or small and gives us the wrong alpha.
Yeah, that's a really good point. That here we are really relying on a reference. We are hoping that if you subtract this reference, in this case, tight binding plus Kachenko-Scheffler van der Waals interaction, then that makes the problem easier to learn. However, if your model qualitatively fails, in that case, the difference could become unusually large in that case. So you can make the problem much more difficult. So yes, that's one of the limitations, even though I would argue that practically speaking, tight binding actually works rather well with some dispersion for CHNO type systems. And of course, if you add halogens, that's where you can really start seeing the models break. But yes, that's a fair point. Is there another point that anybody would like to raise? Jamie?
Yeah, I was just going to say that I guess if you're splitting the force or like the system into intramolecular, intermolecular, I guess if you have greater correlation between those two bonding types, then it might sort of, you know, not be a good approximation.
Right. All right. So let's say another way of thinking about this, the same thing that Jamie has said is, let's say you have two succinic acid molecules, and I don't know how good your chemistry is, but they will, okay, let me make it simple. What if there's a reaction between two molecules? Let's say they start sharing an atom, or, you know, in that case, would you be able to really say whether an atom belongs to molecule A or molecule B? No. In that case, a molecular representation, you know, or let's say at high pressures or in reactive conditions, your system could lose its molecular identity. You know, there are many systems that actually cease to become molecular, like hydrogen becomes atomic, phosphorus as well. Water can become atomic as well, you know, at some point. And in that case, something like this may be very difficult to work with. You know? So that can almost become a bottleneck. You know? But again, for a large majority of practical applications, you know, mainly pharmaceutical ones, you will be able to work with such, you know, a splitting. All right. Okay, so is there anything else that anybody wants to comment on here? Okay, so let's move on. So in the next slide, what I'm going to show is something that I have worked on, you know, where what I really wanted to do was, if we go back here, is to get slightly higher on the rugs of this accuracy. And the approach was to combine machine learning potentials, you know, with path integral molecular dynamics to include, let's say, all sorts of effects that one could see in some of the molecular crystals. And of course, to start, we chose relatively simpler systems, you know, which I would get to. But we really had to come up with an entire workflow, you know, and I hope this will be clear because we did it in 4 steps. So one thing that we really wanted to eliminate here was that since we were using, because for molecular crystals, you need generally need a sophisticated level of theory. And we were using all electron hybrid functional plus many body dispersion, which is very expensive actually. So we really wanted to avoid, you know, performing ab initio MD to generate a training data. So what we came up with is something that combines the previous 2 approaches, where we performed NVT simulations with a lot of perturbations at a tight binding level, you know, density function type, the same that you saw. And that creates a huge data set, you know, of perturbed and equilibrium arrangements of systems. And in this case, we also use path integral molecular dynamics at DFTB level to generate this training data. So for people who don't know, DFTB is a much cheaper sort of empirical, semi-empirical level which you can kind of work in the same way as density functional theory. So you don't really compute your Cornsham orbitals in this case, you just have to do matrix inversion. So this is a much cheaper method. So we use this cheaper method, which has been shown to be okay-ish for these systems, you know, and generate a big training set. And from this very large training set, you know, we again perform this feature selection, configuration selection. We did not use the same approach as I discussed in the first slide. If you were to ask me to do it again, I would definitely use, you know, a committee-based approach. But the main idea is that you use a lower level of theory to come up with a huge data set, and then you select the most important configuration on some of them. You collect the configuration of different polymorphs, you know, And then you train a single model for these polymorphs. And then you use these to perform path integral molecular dynamic simulations. And with that, you can predict Gibbs free energies. This will include anharmonicity, quantum nuclear effects, thermal expansion, everything. Because yes, that's the beauty of these kind of simulations. And finally, we also kept the possibility that these models may not be correct, So there has to be a cheap way to correct for the errors of the model. And the way we did that was something called free energy perturbation, where you could think of it as just from your simulation, taking a bunch of structures and recomputing them at DFT level and computing and just recalibrating the differences. Yes. So the systems that we really studied, and I really think I should have shown you a few of the images, are 2 polymorphs of benzene, then some polymorphs of glycine and succinic acid. And we were able to, let's say, at least using this framework, compute almost exact free energies at PB0 MBD level, And what we did was that we used these to compare more approximate methods that are used within literature, just to understand what kind of errors that they give. And we found that something like a quasi-harmonic approximation, at full hybrid functional level would actually give a good agreement with the exact results. However, cases where you mix and match, for example, you take one hybrid functional calculation and you get your volume, etc., at a lower level, we found that actually can even give the qualitatively wrong result in this case. So yeah, long story short, this was one of the approaches where we try to say, well, if you have a particular system, let's say that somebody has already done the lower levels of structure prediction and given us, let's say, 10 polymorphs, and they want to know what are the free energies. So for these 10 polymorphs, we can adopt this approach where you first do tight binding DFT, get a load of configurations, and then sub-select, a smaller fraction, perform DFT calculation on them, and train a single model for the polymorphs and so on. And yeah, we saw that we got a very good agreement with experiments in all of these cases. And again, because we did not make any approximations in our sampling, any disagreement with the experiment can be traced back to the potential energy surface. Unlike some other approaches, like if you take a harmonic approximation, you may not be sure whether the disagreement arises because of the harmonic approximation or the density functional. All right. So again, does anybody have any comments here or questions? And again, what could be the limitations of such an approach? Well, just because I have worked on it doesn't mean you cannot highlight the limitations. I'm very open-minded. Feel free to. Okay, I will mention a few of them. Again, some of these are related to what we had seen before, where if your density function, if your surrogate model doesn't work very well, then the structures that you generate may not be related to the actual system at hand, So in that case, you might not get a very good training set. So the configuration may not be representative. And the second thing you could say that, well, what happens if you choose a very complicated molecular crystal like an active pharmaceutical ingredient? Would you be able to perform very high level periodic DFT calculations with a hybrid functional description as well as many body van der Waals? And that really could be an issue. So in that case, I would say there are things to be done in terms of how do you generate your training data for an extremely complicated molecule, and do you really have to perform DFT calculations for such large systems, such complicated systems, or is there a way in which you can either build these models at a lower level of theory and then improve them with some high level calculations and so on? So these could be some of the limitations here. Anybody else has any comments here? Well, let's move on then. Well, this was just a prediction of a few relative free energy differences, but the same strategy can be applied to compute phase diagrams as well. There's a very nice paper where, for the first time, maybe the phase diagram of water was computed at DFT level or a hybrid functional level. For example, here is the experimental phase diagram of water, and for instance, here is the machine learning potential prediction along with the quantum nature of nuclei. And as you can see that this doesn't include any empiricism in the model. And you can see that largely it captures the phase diagram correctly. You have a very good description of ice, of hexagonal ice and liquid phase boundary as well as liquid and that phase boundary. And you see that it qualitatively captures the right phases. Of course, the exact phase boundaries are not captured really well in this case, and some of the phases are missing. But it is worth comparing these with empirical force fields. And you would see that in some cases, force fields that could actually do better than density functional theory, because many of them have been trained on relative stabilities of ices or relative stabilities of water and ice and so on, or these properties. But overall, I think it is still an achievement that you could really get entire phase diagrams from scratch with a relatively good agreement with the experiment. Again, some calculations like these would really be impossible at straight DFT level, and machine learning potentials really allow you to compute these. And particularly by for example, in this case, they even managed to do it at 3 different levels of theory. And here you, for example, see what happens to these phase boundaries as soon as you swap your density function level. All right. So, and in the last bit, I would just share this slide on nano-confined water. Again, another phase diagram that I have worked on. And in this case, what we really have done is that we have taken one molecule thick layer of water sandwiched between graphene sheets, and we have tried to compute what could be the phases of quasi 2D water. And as you can see that you can have 2D hexagonal ice, 2D pentagonal ice, flat rhombic ice, square ice or flat rhombic ice. So you can see that these form rhombic structures, and all of these structures are not seen in bulk except for the hexagonal motif. These motifs are not really found in bulk. And the real power of these potentials is that you can really simulate all of these things at finite temperatures. You can also simulate so-called coexistence simulations in which you have half solid and half liquid. And with that, you can trace what exactly is the solid to liquid melting phase boundaries and so on. So some of the interesting things that we found using actually performing molecular dynamics and things at finite temperature is like the existence of this so-called hexatic phase. So just like in regular 3D space or 3D world, you have a solid and a liquid and a gas phase. In 2D, if a solid goes to a liquid, it could go via a so-called hexatic phase. So just like a liquid phase can be seen as an intermediate between a solid and the gas, right? A hexatic phase is an intermediate between a solid and a liquid, and it is known. And let's say using pen and paper, you can show that a 2D system should have, with the short range potential, should have a so-called hexatic phase. So long story short, what we found is that water can also exhibit a so-called hexatic phase if you have a 2D lattice of water. So if water is sandwiched between graphene sheets, it could potentially form this phase, which is really characterized by, it's a disordered phase, but it's not like a liquid. In liquid, you would have an overall flow of water molecules. But in this case, as you can see, water molecules rotate, but they do not really translate. The system doesn't translate together, or it does extremely slowly. And in that case, you get this so-called interesting hexatic phase, which is neither a solid nor a liquid, and it comprises of rotating water molecules and so on. And finally, the last bit I would like to show again relate to this phase diagram is that these potentials are very well capable of breaking bonds, and that's really an improvement over empirical force fields. And again, that's an improvement over DFT, which usually takes a long time to, you generally need long simulations to be able to see spontaneous bond breaking. What we found is that when you have water in 2D, you can get, and if you apply some pressure, for example, if at 2 or 3 or 4 GPa, you see that water molecules spontaneously start dissociating. And for those who are not really sure what these pressures mean, let me just tell you that bulk water would not dissociate up to much higher pressure. So what we really see is that 2D water could actually exhibit a much higher propensity for dissociation. And for example, here is just some water, some oxygens shown in red. And in black, what I've shown here is the diffusion of just one proton. And you can see that the proton essentially hops from one water molecule to the other. And if you compute the ionic conductivity of the system, you would see that it exhibits extremely high ionic conductivities. For example, lithium-ion batteries currently exhibit between 10 to the power minus 3, 10 to the power minus 2 Siemens per centimeters, which are currently used, let's say, in your phone. Ice at the same condition would exhibit 10 to the power minus 5, somewhere around here. While we see that water can exhibit a much higher ionic conductivity. And hopefully we think that this could be useful in future for some technology. Yes, and that was the entire phase diagram that we were able to compute. Again, only with the help of some machine learning potentials, because they really allow us to perform these extensive large-scale simulations, explore long simulation times, all possible structures, simulate, let's say, big supercells with half solid, half liquid to get phase boundaries and so on. Right. All right, so that brings us to the end of the whole thing. And I hope I was able to give you a more practical set of slides on machine learning potentials and their applicabilities. And with that, I would also like to ask if you have any questions, we can have some more discussion right now. Please, questions, if you have any. Hey.
Hi.
Yes.
I was wondering what benefits one could get from relabeling in your data set a certain species. Because you currently only build up these neural networks by element type, but there may be different oxidation states, or specifically, basically, that kind of thing.
Right. So by labeling, would you mean something which encodes the electronic state of your atoms?
Yeah, or just the fact. So let's say you either, well, in my case, sorry, this could be boring for everyone else, but
right.
If you have a polaron that moves around in the layer, the distortions are very small. You could do symmetry function kind of checking.
Right.
You could have very fine grained symmetry functions so that you pick up the small distortion. Or you could just change the label on the site that hosts the polaron to a different element, and then it won't. Would the machine learning be able to? What was my concern would be with all the other iron atoms compared to the one atom that hosts the site, would you lose the ability to track the forces or learn the forces, etc.?
Right.
Have you ever had to?
Yeah, that's a really good question. I guess maybe I can explain to the others what a polaron is. So let's say you have a crystal structure and you inject an additional electron. So in the presence of defects or small deformations, you could see the electron getting localized in a particular region, and that's called a polaron. Would you say that that's an apt description at a high level?
Yeah.
All right. So I guess Kit's question is that, okay, you can really do equilibrium conditions where, or neutral system, what happens when you inject additional atoms? Do you need to, let's say a polaron can be seen as a pseudo particle in this case. Do you need to include explicitly these pseudo particles, or can they be implicitly treated in this case? And I would say actually you can do an implicit treatment of these pseudo particles. So all you have to do is, instead of, you need to train two models in this case. In the first case, the first model should be a neutral model, and the second case you should have one additional electron, right? And for these two systems, you should train two different models. And you don't need extremely fine-grained symmetry functions, because all of these symmetry functions generally they have a width, right? So if you're, maybe we can go back. So if your atom moves from here to here, it would still feel a difference in the signal, right? So you don't need a very fine set of symmetry functions. It will be able to detect, and it will map these differences, in the local structure to the energy. So I have personally worked on not a polaron, but something similar, where we inject an additional electron in water. So that's called a solvated electron. And in that case, we did not have to change anything. The same model that worked with for water, the same symmetry functions also allowed us to do water with an additional electron. So I know you have written an email to me, Kit, on this, and I will respond to you. I'm actually attending, some sort of event. It's a friend's wedding in a tiger reserve, to be very clear. So I'm a little limited in terms of my internet and work. But yeah, I will get back to you with more specific feedback on this problem. Does that answer your question? Or
yeah, I think it does.
All right.
Yeah, thank you.
Yeah. Anybody else has a question? Yes, please go ahead.
I have a quick one. Could you go to the slide?
Can you repeat?
Can you go to the slide where you show the different types of approaches, like the feeler, Paranello,
right,
the gap?
This one? Yeah.
So I recently, yes, I forget the name. Anyway, there was someone who was talking about Allegro, which is basically building on Necro, right?
Yes.
What is kind of the next steps? So is there already something, I would say, in quotes, more advanced than Maze, like where you have the spherical harmonic based recursive? Are there, like, what are the approaches people are thinking of proving those?
I'm not sure if I'm getting your audio correctly, but I guess your question is more along the lines of where are these approaches going towards? Is that a good way to understand your question?
Yeah.
Right. So I think maybe I can take the time to also discuss what are the limitations of each of these approaches. So, for example, the Baylor-Pinello approach, I would say it has two limitations, or let's say three limitations. One of these limitations extends to all of these approaches here, which is that they are all short-range models, right? So none of these models have explicit long-range character. That is a problem. And generally, you have to supplement these short-range models with some other long-range treatment. All right. Now, Baylor-Pinello framework has two limitations, in my opinion. The first one is that, yes, you have radial and angular symmetry functions, but with this, you can show that you treat a maximum of three-body correlations. You can build systems where two configurations have different energies, but if you compute the symmetry functions, they would have exactly the same representation. So that's a problem. So one could say that if you go from your space of positions to this space, you could have some degeneracy where it's not really a one-to-one mapping. Many structures can give you the same sets of symmetry function, So that's a problem. And again, these problems these are evident in more complicated cases. Same is the problem with the gap model, that it has, that was the first problem. The second problem is combinatorial explosion of your radial and symmetry functions with the number of species, right? So here, the first problem is on the accuracy of this representation, and the second one is the cost of developing it in the limit of many number of species. Gap has the same problem, so from the perspective of information, these three have exactly the same. Gap has an additional issue, which is that because it's based on kernel ridge regression, its cost can also scale with, if you don't do it in an extremely smart way, on the amount of training data. There are ways to get around this, but in general, gap models can be more expensive than Baylor Pinello and DeepMD. So that's one of the things. But again, the amount of accuracy is exactly the same. And all of these will have the same problem of combinatorial expansion, explosion, right? Now, SNET, it's a very simple model, which only uses two body distances, and a more complicated neural network scheme. It is a much more flexible model. It can even deal with features which do not have the same dimensionality and so on. However, it is limited by its ability to, let's say, treat n-body correlation. So it won't be the most accurate model out there. Now, up until this point, most models had two types of errors. The first one was the combinatorial expansion, so two limitations, and the other one was its accuracy because of limited body order. So between these, there was a lot of theory work in the field, which tried to really understand how all of these are related to n-body correlation functions and how you can build greater body order representations. And that's where Anyquip and Maze came. These were not the first ones. There were many in between, but let's say these were the first ones which are directly usable and have very nice codes available. And this allows you to get arbitrary accuracy. So in principle, there is no error within Anyquip. The only error arises from the cutoff and the local approximation. So if you treat all the atoms in the system, this in principle has no error. Same here. You can keep increasing the number of layers and you can keep increasing the body order. So systematically, these two can learn everything. The difference between this and this is that this again has this combinatorial problem, where its cost really scales with the number of chemical species. Maze tries to address this problem, but not in an exact way. So let's say that if you have only one type of atoms, then this is exact. But as soon as you have more types of atoms, Maze will give you efficiency at the cost of some accuracy. All right. So this is where the field is really getting towards. Now, what you really want to get is something which is both cheap and accurate, And there lies some sort of a dichotomy where models which really allow you to map using very simple things like just position vectors are often a little more expensive. So architectures can be expensive, and for that can be tackled in two ways, either better codes or better supercomputing infrastructure. Like Google is trying to build these tensor processing units, which will hopefully make these much more efficient, and so on. And the other way in which the field is going is to make things applicable to many different chemical species. Like if you want to apply this to proteins, it's not really a plug and play, right? Like if you look at a charm force field or an amber force field, you just take some parameter that's really transferable, you can apply it, and the cost doesn't scale, explicitly on the number of different types of species, right? So generally, this is where the community is going. They would ideally, at least the benchmarks that I see based on my discussions, is that they would really like to develop these models to be able to have transferable models which can simulate, let's say, any system. And you just take some parameters, change them, or you take, let's say, a model of oxygen, combine it with a model of hydrogen, and there you go. You can simulate any other system. So that's where the field is heading towards. So the specific things that we need to address are, how do you reduce the complexity of getting these n-body descriptors, number one, and how do you reduce the cost of representing your environment without this combinatorial explosion. And yes, so for example, the way Allegro, I think you said that works, is that it is much more forgiving in terms of its cost, but its accuracy is compromised. So currently there are approaches which are either very accurate but expensive, which can treat a lot of chemical species, but approximate, or very efficient but approximate. And depending on your use case, you can choose a model. Like for my work, I generally use Belo Pinello because it allows us to get the accuracy that we want to perform all the simulation, and I find them to be extremely robust. But in future, I would really like to probably move towards models which can be applied to systems with many different types of species. I hope this answered your question. All right, a thumbs up. Any other questions? Well, in that case, I think it's almost time. For me, it's time to have dinner, and for you all, it's time to maybe attend another seminar. Or yeah. So yeah, thanks a lot for coming. And again, reach out to me via email if you have any questions. Those of you who have sent me an email, I will respond to you if I'm not eaten by a tiger here. And yes, so in general, yes, so I will type my email here. Right. So yeah, feel free to get in touch with me if you have any specific questions, or if you need more resources and so on. I'll be most happy to help. I may not respond immediately, but I will definitely respond to you eventually. And by eventually, I don't mean after 1 year. All right. Thank you very much. And with that, I will stop recording.